Okay, so welcome everyone to the Quantum BW colloquium. It's a pleasure today to have Vadim Vorobev here as our speaker. And in contrast to the past Quantum BW colloquiums, today we're going to switch gears a bit and talk about quantum sensing and not so much about quantum computing. Quantum sensing as a topic is usually a bit in the long shadow of quantum computing in terms of the popular knowledge, so to say, or popular awareness. But in recent years, there's been a lot of progress in quantum sensing, and there are a lot of research initiatives, for example, QSense of Baden-Württemberg state, and Vadim is doing his research in this topic. A couple of words about Vadim. So he did his PhD in Moscow at the Moscow Institute of Physics and Technology. And then since 2018, he is a member of the Third Physics Institute here in Stuttgart, where he is the subgroup leader of the quantum sensing research. And his research interests are reach from the applied to fundamental physics. And his focus is on investigating and overcoming the fundamental physical limits in quantum sensing. He's focusing on many different platforms for this, for example, the NV center in diamond, silicon carbide, tin vacancies, and so on. And we're happy to have you here, and the floor is yours.
Thank you, Ruben. It's a pleasure to be here, and thank you for invitation. Actually, I think I've done a talk here at Colloquium with Daniel a couple of years ago, and maybe some of you remember me. Since then, we did quite a few new advances, also opened new topics. So I hope today it will be completely fresh, so nothing to be afraid of here. So as you see here, this is kind of a crystal lattice, and this is a crystal lattice of silicon carbide. You see a two-atom species here. And we are working with a color center inside, which have to talk to some other nuclear spins, which we're interested to be sensing. But today I want to talk about the limits in the quantum sensing, and in particular two limits, which are, let's say, the very fundamental limits which we are facing with. And the first one is the standard quantum limit, which all of you should know. And I just want to capitalize on that and show our recent results in this direction, as well as the diffraction limit. And this is a very exciting topic, which means that we are now at the level where we can go beyond what the normal optical microscopy can see, and despite the limits of the normal optics, still uncover what is happening on these scales. But I want to start with like a very large quantum sensors. And why? Because I want to just emphasize that over the last years, the progress in designing them is very rapid, and still the governing principles are the same. Like, it doesn't matter if you take the quantum sensor, which is very small, or very large, the principles are the same. So here what you see is the gravitational sensor, which was published in this seminal paper, in which they actually being able to image kind of layer by layer composition of the ground, where you can, for example, find a hidden over the years house or hidden tunnel, and the precision of this device is on the order of 10 to the minus 10. So this is kind of the state of the art when it comes to measurements of the gravity of the acceleration. And this is also not just accelerometer, but it's a gradiometer of accelerometer. Essentially, it's measuring the differences between the gravitational constant here and here, and because of that, it can cancel all the environmental noise and can be actually field ready. So in this work, they were able to kind of deploy here this just in the backyard of the institute and roll it around and see if they can measure the tunnel of the size of 2 meters underground. That's quite amazing, I would say. Two other examples of the quantum sensors without which we cannot imagine nowadays life is, the first of all, is the optical clocks. And because all of us are using GPS navigation and the positioning system, as well as the synchronization of all our clocks. And the other one is the gravitational wave detector, LIGO, and the other systems which are now positioned worldwide, which are also quantum sensors, and they are huge. They're several tens of kilometers in size. And they give us now the access to the very fundamental things about our universe, how actually the the fabric of the matter can propagate through the space, and this is quite exciting. But you can imagine that the quantum sensing part here is somewhere here, and the light, which is going back and forth, is being able to detect the deflection of the mirror here of about 10 to the minus 23 relative position. So this like much less than the wavelengths, which is diffraction limit. Okay, so there are many other examples as well, and this is just the schematics of what is happening inside the LIGO. You actually have two cavities where the light is amplified, and the mirrors here are suspended on some like pendulum system. And what is also happening is that these mirrors, they feel also the pressure of the light, and whenever you measure, you're already obtaining some sort of this back action effect, which is another important ingredient of the quantum sensor, where you cannot measure without disturbing. And this is happening on such large scales. Of course, you can also use other types of sensors on the macro scale, but as well, all of these sensors can be miniaturized, and for example, the optical vapor cells can be miniaturized and put in a solid state, and what we now call as like color center field is quite rapidly growing, and it's in particular promising for small sizes. But superconducting qubits and squeeze magnetometers, they also could be miniaturized and put on an apex of the scanning probe, which was also nicely demonstrated in this work. As well as there is interesting direction in combining different sensors. For example, here, the mechanical MEMS quantum sensor and the atomic vapor could be combined in a way that they kind of complement each other and make the performance better. Out of these sensors, as I said, we are interested in these color centers, and they are phenomenal because they allow you to reach this left corner of the overall chart of performance. So we are interested in the very small sizes, as we are interested in study of the functional matter on a nanoscale and, for example, single cells and proteins. So here we go to this corner, and we see that this is the fundamental limit which can be achieved with all of the sensors in terms of like energy resolution available. And as you see that the squid technology is like outperforming everybody at the micron scale, and the atomic vapors outperforming everybody in the millimeter scale, while the nanodiamonds and the cantilevers and so on, single and V center, they outperform everything in the nanometer scale. So because of that, this gained enormous attention of the research community, and there were several, breakthrough experiments done so far. Have to say that color center and diamond, in particular quantum sensing, already become interesting for industry, but it's not yet widely accepted, and there are several challenges still which are stopping this. But still, like these are just a flash of some exciting applications, in my view, which are already there, and in particular, the robustness of the diamond itself and the fact that it's the hardest material on Earth can allow to integrate the color center, for example, into the anvil cell, diamond anvil cell. And the diamond anvil cell is actually the perfect condition to study new materials, especially at high pressure and like extreme conditions. For example, the quest for searching for room temperature superconductivity is related to this search. And because the superconductivity is also related to magnetic properties, you can just directly visualize them with the quantum sensor. So that's the one exciting direction. Another one is, of course, integration of navigational inertial sensors and magnetometers in the solid state, like work towards MEMS, kind of combination with MEMS. Another important field of research is scanning probe in V. So this is exciting because the IFM atomic force microscopy is quite well developed, and if you just equip every setup on Earth of IFM with a quantum addition to that, you immediately get a scanning magnetometer, which is quantitative and doesn't rely on any calibration and so on. So this is also quite exciting. And last but not least is this direction which is related to biology and imaging whatever processes happening in living tissues and cells. As NV center and nanodiamonds are also quite reliable and robust, you can, for example, look at its rotation within the cell. You can look at its motion. You can look at you can track the motion of the different nanodiamonds, for example, within the cell. You can check the magnetic field response to this. You can also see how it reacts to electric field and concentration of different radicals, temperature inside, and this is an active field of research right now. But what is, like, if you want to talk about NV center, so this is just a recap. I guess many of you already know this. What is NV center in diamond? So if you take a piece of diamond and look very closely to it, NV center is actually what makes it look pink. So if you have a commercial or natural diamond on your ring or so, if it has a slightly pink color, this is because it has a lot of color centers like this. But if you just take one of them and look at its properties, it looks like a molecule which is frozen inside the solid lattice. And this allows it in a wide band gap, which is 5.5 electron volt, inside a diamond, form just a two-level system, which is optically active. So you can excite it with green light, for example, and then you can collect fluorescence. So this fluorescence is then dependent on spin state, which is in the ground state. And you can also address this in a microscope with a laser, scanning laser, and you can find singles if your sample is clean enough. And if you apply some B field, the different levels in the ground state start to Zeeman split. And this is the main idea behind this magnetometer, because if you start addressing this transition from 0 to 1, you will start to see a dip of fluorescence, because fluorescence strongly depends on the whatever spin state in the ground state. And you just simply observe the motion of this peak with respect to the frequency, and this will directly relate to the B field. You can also try to coherently drive it, and with that, people realize a qubit. It's a single qubit system which can be initialized by shining the light, and with driving of the microwave, you can just perform a Rabi oscillation. The coherence time of this system, even at room temperature, is already in the order of milliseconds if it's in a pristine bulk diamond, and this is quite remarkable compared to other semiconductor and solid-state platforms which suffer from phonons a lot. So all of the quantum systems in the solid states we know so far have to be cooled down to 4K at least. And this is because the phonon is mixing all the time. For the NV center, it's not the case, and even at room temperature, it's decoupled completely, and this is, I think, one of its key advantages. So let's go further. We want not a qubit, we want we want a quantum sensor. And the quantum sensor, any protocol for quantum sensing, as I told you, being this a gravimeter or interferometer like LIGO, or a spin quantum sensor, or maybe optical clock, is a Ramsey protocol. So Ramsey protocol is a very basic thing, which consists of initialization of the system, applying a pi half pulse. As you've been in many quantum computing colloquium, you know what it is. So then you have the sensing period, which is just a time tau, during which you let the system interact with the environment, and then you apply another pi half pulse to project it back to the quantization axis. And if you just visualize what happens here on the Bloch sphere, you will see that the projection, the final projection on the z-axis, have to oscillate as a function of tau, or as a function of applied B field, or any other perturbation you apply to the system. Any questions? No? So, by the way, if you have any questions, I think best is just ask straight away, so that we can have some small pause. Yeah, let's go on. This is what is happening here. For that to work, the requirement is that the quantum system is essentially a qubit system. Okay, so you have to have this kind of reduced de Vincenzo criteria satisfied, and it has to be able to initialize. You have to be able to read it out. You have to be able to apply coherent control, and it has to be sensitive to value you want to do. And then, of course, you cannot do it once and then just have your result. You have to do it many times, because in any of these kind of single-shot experiments, in the end, you are just getting 0 or 1, which is the single-shot answer from the qubit. So you project it in the end. And this is not enough for you to understand what was the value, because it's binary, and you want to have a continuous response. So what you do, you repeat it many, many times, and you obtain the probability. So if you obtain this probability, this is what happens. You have to then apply some sort of estimation protocol, and this estimation protocol depends on the interaction which you encode. In the end, the scaling which you obtain is exactly the standard quantum limit I was talking about. So if you start repeating this many, many times, n times, the precision with which you go is scaling like this, and this is the standard quantum limit. If you do this for NV center in diamond, so this is the theoretical prediction from 2008, when this field was just like starting. And you see that the sensitivity for ensemble was reaching femtotesla, even beyond femtotesla sensitivity, with some optimistic going even this. And this is enough to measure the brain signals. So if you think about it, fundamental limit is actually not limiting you to measure the brain. And this is like a room temperature system. You can just walk with it, and this was really very exciting for the community that it can be so precise. Unfortunately, the real life is a bit harder, and the current map of sensitivity looks like this. So you see that NV is like, first of all, the white line is the boundary for classical sensors. So this is where the heritage technology stuck, and it basically cannot cross it. So it's on the order of like nanotesla sensitivities, and this is what, for example, Overhauser magnetometers and some this oscillating flux gate magnetometers are being held. So they are still good. They are being used, for example, in fields to explore the mines, and you can hang them on a drone and fly with it, but they hardly can break this limit. So now this is the new generation of quantum sensors, and you see that the color centers are here. There are squids here, which are a bit more bulky, and there are like serfs, which is even more bigger construction. It has this gas cell, which cannot be miniaturized even further. Yeah, so then you see that the projection limit is somewhere here. So it's still 3 orders of magnitude below. And this is the current kind of challenge, how to push this even further. You can also look at this performance from the other angle. And this is, for example, if you want to look into the sensitivity of the color center in particular to nuclear spins, like if you're interested in the NMR measurements with that, you can plot this like size versus sensitivity and put here a line which is representing the how many magnetrons you can sense within the certain time per hertz. And you can see that if you have a very small sensor, you can actually come very close, and the sensitivity, like the bad sensitivity, is enough to measure already single proton, which was demonstrated. While if you have super sensitive sensor, but it's large, you hardly can even measure like 1,000 of electrons. So in this sense, size matters, and the smaller the better. But still, you see that we are barely reaching the limit where we have to be super close, while the normal kind of scale of membrane is on the order of 100 nanometer, and nothing is actually here. So there is no sensor which can be used to measure NMR, for example, of membrane proteins. And the people are still working on that. And I will show you now a couple of results which we do in this direction. But if you want to just measure, for example, single molecule, this is already realized and this was shown. This is hero experiments, of course, but this is what was done. Yes, and the main reason why this is the challenge, because the way to do this is actually not to use single sensor, but many sensors, because then you can amplify your signal. And this is what the initial blueprint was using, like many sensors, and the scaling is just improving a square root of number of spins, but it's not happening in the real life. So if you take a single NV center, people realized already in 2010 that you can have this absolute readout. So they call it universal readout. This is projective measurement readout. And the information you are getting from a single NV is binary. So you can have a spin projection noise. You either get 0 or 1. And this is what's shown here. Of course, you have some noise. But in general, you can filter this out and already have like a full qubit kind of operation performance. However, if you take ensemble, this is generally not the case. And for most of the ensemble realizations so far, the reduction in the performance is on the order of 100. So you're losing factor of 100 immediately. And this compromises this performance to the level that it's not kind of applicable yet. But in principle, we were curious about reducing this additional noise. So this blue noise here is a technical noise, which is hiding our quantum signal. So the quantum signal is just information about the spins. And the blue one is, and the spins are our quantum sensors, while the blue one is actually the photons which are they emitting. So the photons in this case are not quantum sensors, they are just classical carriers of information. And because the photons are intrinsically noisy, they have this shot noise, they hide the useful information. And normally this blue, let's say Gaussian broadening washes out our signal so much that it's not anymore as sensitive. You have to average it down so long and so on. So what we did here in this work with Ruben is that we tried to apply the similar-like idea. So we try to find the nearby ancilla qubit and swap it many, many, many times, such that if you repeat this protocol long enough, you start to kind of reduce this blue noise, additional noise. And eventually, you start to feel the actual quantum noise which is inside. So the idea is shown here. We're also using the sequence with each NV center has a nearby nitrogen nuclear spin. And the details are not that important, but if you apply this and you look at the noise distribution, so this is just a distribution of Gaussian statistics, you start to see that if initially it was kind of broad and was broadened, upon application of more and more repetitions of that, you kind of collect more and more photons. And since this is just a shot noise distribution, it has a Poisson width. The relative width starts to decrease until it reaches this new level. So this new level is related to the spin projection noise level. And this is what we are now achieving. So the position of this level also related to number of NVs, as like we have a standard quantum limit. And from knowing where it goes, we actually know how many NVs we are measuring in our ensemble. In this case, it's on the order of 100. And you see that the square root of n is on the order of 1/10, which matches quite well. So now you know that if you measure this ensemble and you perform, for example, its Rabi oscillation or any quantum sensing protocol, you don't have like just an average blob, which you have to then average, but you see more like a pointer, which is very sharp. And this gives you then almost like ultimate precision you can have with this sensor. Interesting also is that as basically we have 100 sensors, which we measure instantaneously, all of them are like a towing course, right? So all of them have probability to be up or down. And the final distribution is Gaussian, is like a central limit theorem. And now what is interesting is that the width of this Gaussian depends on the probability to be 0 or 1. Because imagine if you have all spins probability 100% to be up, all of them would be just at the extreme position and there would be no distribution. So this is would be the extreme case of having no shot noise, so to say. And this is visible here quite well. So you see that if we first initialize all the spins and then we start a Rabi oscillation, the width of the distribution also starts to change. And this is exactly it. So it's basically like a classical coin toss. What I'm talking about is also shown here. So this is the actual like photon distribution we are getting. You see that if we do nothing to the spins, so they are just left thermal, so they are just randomly polarized, they more or less follow just a binomial Poisson distribution. However, if we polarize all of them, this width starts to decrease. So this is the difference between them. And then what we can try to do, we can try to correlate all the spins. So we can ask them to say either all of them are up or all of them are down. And this makes them more like feel each other and being correlated. So if one of them is projected up, all of them are projected up. And it's not yet like this GHG state, but it's some sort of correlation which we induce. And if we apply that, you see that they start to behave like a giant single spin. So they start to have this splitting, which is usually a signature of being like quantized. You have either 0 or 1. And this is the effect we try to measure here. And interestingly, since it's especially prolonged object, the ensemble which we measure, with that you can also try to approach not just measurements of single quantities, but you can measure the spatial correlations of two physical quantities. And this is, I think, also quite inciting in a new result. Of course, you can also, since you have now universal readout, you can try to approach a reconstruction of the full tomography of the ensemble, and this is a challenging task, but I will not go here into much details. Yeah. So now we can finally see what the effect it made on our sensor performance. So if we estimate number of readouts, essentially like how many photons we keep collecting from our sensor, up until certain point it starts to improve, until which we reach this plateau, after which it's just been saturated already and you just start losing time. So it's not helping you to improve the sensitivity. And you see that we started somewhere here. So this is like a 100 nanometer focal spot. And we have on the order of like 1 nanotesla sensitivity, which is shown here. And then with this, we go like 10 dB amplification, which gets us to the level of 100 nanotesla, sub 100, oh sorry, picotesla. And this is where the level at which now we can start to sense single protons, and this is kind of the target application we have in mind. But this is not only about sensitivity, because it turns out that yes, we can improve sensitivity to, let's say, standard quantum limit, as I showed you now. So it cannot be better than this if you don't use any more like quantum enhancement. And in fact, for this atomic vapor system, this was realized back in the 2010s. And after that, what they did after is that they tried to furthermore use the interactions between the systems inside. And they try to create so-called squeezing, spin squeezing state, where you, out of this Gaussian blob, you start to increase one of the axis uncertainties, but by cost of that, you reduce the uncertainty of the interesting axis. So if you do this, and you feel already the spin projection noise, you can furthermore improve the sensitivity. In this case, we went by only maybe a few decibels, but this was already quite a big advantage. But more interestingly is that now that you feel the statistics of spins, you open a way to use these spin ensembles as a solid-state quantum simulator, which is working at room temperature. This is quite exciting, and there were just back-to-back 2 Nature publications this summer, 2025, from Harvard group and Berkeley group. And what they showed is that if you have this NV centers in different geometries, they represent a very complicated system. So they have this dipole-dipole interaction, including the near neighbor and also long-range interactions. And this allows them to engineer these interactions in a way that you can first of all create a similar spin squeezing. So you can have a twisting dynamics within your ensemble. But also in the other works, what they showed is that you can also engineer some sort of spin glassy behavior, time crystalline, and so on. However, this is nice because they kind of can control the interactions, but their readout is not yet what we showed. They basically have just a photon shot noise limited readout. And this does not allow yet them to show the intrinsic dynamics. Now combining these two works, actually this could be possible, and this is quite exciting. Now I want to, from this kind of ensembles, switch down to the single spin quantum sensor, and also switch a bit the system. So the diamond is very well known, and I'm here also to advocate a bit the other platform we are studying, and in particular the silicon carbide. So as you know, silicon carbide is a mature semiconductor material. It's wafer scale available, so you can even buy now 12-inch silicon carbide, which is like a pancake. And it also holds the record values for photonic integration, optical cavities, and most importantly, it also has defects inside, which are optically stable and also spin coherent. So we thought it's a good idea to also try to see how well they behave in terms of being a quantum sensor. And for that purpose, we use the color center, which is called V2 center, which is basically just a missing silicon in the lattice. So if you have a missing silicon, you of course again have these molecular bonds and so on, and you can try to optically excite it. And in the past work, we already showed that the spin coherence is exceeding millisecond at low temperature. T1 time is on the order of 20 seconds, which is quite long. It actually accommodates all of the operations you can ever imagine. And you can have quite a nice 99.9999999 readout, essentially limited only by the time you are committed to wait until you collect enough photons. So this is quite a good system. And most importantly, it has a lot of interesting objects around, and in particular, these nuclear spins I'm talking about. This is what we've shown already 2 years ago or so. So here you see that if you start using this electron spin as a sensor, in this system you start to both see silicon and carbon nuclear spins around, and just applying basic sequence straight from NV to silicon carbide, you get straight away like 5-qubit, 7-qubit systems characterized. But you can go even further, and combining the dynamical decoupling plus some coherent radio frequency control, you can open up the way to see up to 20 spins from a single color center. And this also because at low temperature the coherence times is quite enlarged. You can engineer coherent interaction, you can drive the Rabi oscillation of those spins here, and you can even write quantum circuits more like in Qiskit style. So this is already what is happening. And now what we try to do is we try to carefully characterize each line here just to get the answer about like what are we seeing. So if we categorize, we see on the order of 30 spins, each of them presenting single qubit, fully controlled with high contrast. The nuclear-nuclear interaction can be also addressed. For example, here you can use one of the spins as a sensor for another one, and you can, by that, you can spin chain them, and you can create like interlinked registers. So here, what we do, we just use one silicon one, which is here, as a sensor, and we just perform like a Han echo sequence on it, and we recouple the buzz spins to it. So the buzz peak starts to pop up. So if we just sit on one of them and we control this time, as I told you in the beginning, this Ramsey time, the coupling strength comes in and we can see how fast it oscillates. If we just measure this frequency of oscillation, we automatically understand the distance, because this is just dipolar-dipolar coupling between two dipoles. So we did it for like a couple of 100 couplings. So because essentially we see 30 spins, and then what we can do, we can measure the coupling of this to this, this to this, this to this, and like overall 100 couplings, 150 couplings. Now this is a problem of optimization. So it's more like similar to graph optimization problem. So you need to know that if you know the distances between all of them, where would they be in the lattice? So now this is the task of like purely mathematical. And we also did this also, like, we're not the first ones who are doing this. It's more like from protein reconstruction also, and there is a lot of knowledge in the field. And now we can with quite certainty say each atomic location of each spin. So this brings us again to this map. So because now we didn't change the size in this case is on the order of 2.5 nanometer. But what we did, we improved dramatically the coherence time, because we went to low temperature, and we could now have this 20-second kind of interaction time. We are now at the limit of where we can see not only the proton, but we can even see weaker spins like silicon and carbon within the interaction time we have. And this is already not diamond, this is silicon carbide. So now I want to switch to the last topic. I don't know how much time do we still have. 10 minutes? Yeah, so the last topic is a bit more, let's say, mathematical. So not mathematical, but controversial. So it's not like physics, I would say. But it's quite exciting for me. So because you see that in many times you're not interested in the signal which you measure, but you're interested in correlations. So if you look at the Ising model simulation with like Metropolis algorithm or something like that, you see noise. But if you start plotting the correlation of this, you see this. So, and this is what is usually theorists are interested in. So they derive the correlations, the exponents, and so on. For the phase transitions, they do not know what individual pixel is doing. And that's why what is interesting for us is also not to measure this, but actually being able to measure correlation. So more like generalized order parameter. And because of that, many experiments are also, especially the top performing ones, are interested in correlations. For example, you see that the LIGO experiment was successful because they actually have two interferometers on the different sides of Earth, and the signal was correlated. So because of that, they can filter this out from other things. And now in quantum sensing happens on the nanoscale, the things are happening same way. If you have two NV centers, for example, if you have two quantum sensors, you can correlate the noise coming to them. And you can distinguish if it's, for example, coming from local noise source on one of the NV centers, or is it something coming from globally from outside. So this is sometimes very interesting, because you can also create, for example, entangled states of two of them, and they can be intrinsically insensitive to global phase, but they could pick up a phase, for example, if there is a gradient. And this prolongs already the coherence time on them. In this case, 1 + 1 is more than 2, what you can say. However, usually, like if you know this quantum enhanced sensing ideas where you create like a GHG state, the problem of this GHG state is that it decays faster than each of them, because it's more sensitive to what you want to measure, but it's more sensitive to noise as well. In this case, you can engineer it such a way that it's insensitive to the global noise. In that case, it doesn't decay, but it would be sensitive to noise on one of them. And that's what people do. Here now also in the bulk systems, when you can actually confocally distinguish them, you can measure two spots. But also in a nanoscale where you have the scanning probe, and inside the scanning probe you have already two. So the question we had to address is, how do you distinguish signals from each of them? Because most of the time you just get a combined readout channel. So you have just one optical channel, electrical channel, whatever, where the signal from both of them is coming together. And this is also the case where you have, let's say, a diffraction limited readout. So you have one spot. This is your diffraction limited spot. It's on the order of lambda half. And then two systems emit the photons inside it, and you cannot distinguish who is who. So this is the idea we want to understand. And in this case, we have two NV centers, for example, which are sensitive to this Ising chain or whatever correlation we want to do. But we want to know not just the average signal from both of them, we want to know individual, and we want to also know the correlation of them. Yeah, so this is the setup. You see that you have two differently aligned NV centers, for example. The ODMR on each of them can be separated because they point in different directions, so they have a different Zeeman shift. So this is the first good news. You can distinguish them in the ODMR spectrum, which is a good start. Now, what is interesting is that in the optical fluorescence, they would behave like this, depending on polarization angle at which you shine. And this is the feature because if they are differently oriented, they react differently to excitation. And this already allows us to make some distinction. Because now what we can do, we know that, for example, the blue one is brighter than the orange one. And if we start to measure them projectively, we know that the blue one, for example, it comes from being very dark to a bit brighter. And the orange ones, it comes to being very dark to slightly brighter. So now the combination of these two jumps, it forms like a 4-digit jump process. And you can have like a histogram where it's not just 2 blobs, but it's 4 blobs like this. This is already quite good because now you can say, I know that in this column, both of the systems are bright. In this column, one of them is bright, the other one is dark, and so on. But how do we get like a bit more quantitative about it and not just, qualitative measure the dips? For example, this is just one of the histograms we are getting, like this is number of counts we are getting, and this is, in this case, it's not yet spin information, but this is just charge state information, which is quite established technique. If you want to know about the spin, you need to first convert the spin to charge, and this was also done for single NVs already in 2015. But we now try to combine these two things together. So we try to do spin to charge, and after that we are reading out this demultiplexed picture. And if we do it just on top of our head, just look at the column height in these two bins, because this is actually where the two NVs are separated. We immediately can, out of this combined ODMR, see two deconvolved ODMR. It's quite neat. But if you want to do it quantitatively, for example, you want to calibrate what is your expectation value of the spin operator, the E's, and so on, and being very precise in numbers, you have to do a bit more. And of course, nowadays, the best tool to go is like using the neural network. It's quite established now in many systems, and the only thing you have to do is you have to give it a way to calibrate the propagation, and after that it can guess what would be the state. So what we're doing, we are trying to drive a typical Rabi oscillation where we for sure know what will be the states, after which we are obtaining these photon histograms, and we train the whole system on that. So I guess the compound of the nano network is quite standard in the field. We played a bit with parameters, but it was more or less settled and it was already working. And this is our Pearson training score. It's quite good already, and we decided to just give it a go. So here you see that this is the extracted observables of SZ, which is the spin operator, for two spins observed at the same time. And here we try to apply some pseudo-random sequence where we want to model the case where we have correlated noise or uncorrelated noise, and we are looking at the correlator score. So it works quite nice. Interestingly enough, here, if you apply pi half pulse, and then measure, you destroy the correlation. So if you apply the same pulses here, and then you project to Z, if you don't apply a pulse, of course, both of them are up, and then the correlation is still positive. So sorry, both of them are down. Correlation is still positive because minus minus gives you plus. And the same happens if you apply a pi pulse and so on. But if you apply pi half and then project around Z, the correlations are fully gone. So and this was also quite interesting to understand how it's all happening, but it works exactly how the theory predicts. Yeah. So then, as a summary, I would say I told you about the limits which we have in quantum sensors, in particular within these centers. And here I showed you the work of enhancing the sensitivity down to the fundamental limit of standard quantum limits, spin projection noise, for the small ensembles of NV centers, which is quite exciting now. Another thing which I was touching is enhancing the sensitivity of sensors by going to low temperature, increasing coherence time, and also being able then to resolve, let's say, sub-nanometer scale nuclear spin cluster, and being able to use machine learning approaches to deconvolve or demultiplex the signal coming from, a non-resolved spot. And I think these two kind of combinations would be interesting to combine and study further. Thank you for your attention.
All right. Thank you, Vadim. Now the floor is open for questions. Are there any from the audience? If not, then I will start with one question.
There's a question from the online audience.
Okay, then
So my microphone was off, right?
Okay, the question is, thank you for a very interesting presentation, Vadim, first of all. On slide 7, you have mentioned the NV center-based magnetometers still have some bottlenecks until commercialization. What are the main ones? The main bottlenecks?
The main bottlenecks. Yes. So if you start to think about bottlenecks, I would say that having kind of ensemble magnetometers with good enough spin coherence properties and readout contrast is good, is what is missing, like reliable supply of diamond samples, for example. At the same time, the periphery is still undeveloped, so you need the readout methods are such that you rely on the electronic noise rather than the photon shot noise, and of course not even spin noise, projection noise. And this is, for example, what was already solved for atomic vapor cells and surf magnetometers, where the readout is using the resonant laser. It's much more efficient, and you have almost 100% contrast, and you're really probing down to this fundamental standard quantum limit. And this is the challenge, I guess, for NV, because even though it's working and it's compact, but the readout is far from limited by fundamental limit. So that's why these initial proposals are not yet satisfied.
Maybe I can follow up on that question as well, because you usually within the community, you sometimes hear that quantum sensing is a lot closer to, let's say, market readiness compared to the quantum computing. What are your, let's say, if you look into the glass ball, what are your predictions like for the coming years? Where do you see big technological leaps in terms of quantum sensing? Which platforms or which applications are the most promising ones?
Yeah, so thanks for this question. I think indeed these gravimeters are surprisingly interesting. I guess even just if you say like social applications, like commercial applications, of course also governmental, like accounting for the like inspecting the territory which you have and so on. is quite nice. And I honestly don't know any other analogous technique. Also, navigation-wise, recently there is a breakthrough in using these magnetic maps with high-precision magnetometers, like movable atomic clocks, and like exceeding the precision of current atomic clocks, but also using them more, let's say, widened. Scanning probe NVs are quite abundant already, and there are many startups doing this. People are using the diamond color centers for investigation of the current leaking from the batteries already, which allows you to improve over the whole sensor. And this, because you want to measure the capacity of the battery, but if you measure this by integrating the current, it's like a MEMS accelerometer, it diverges over time because you have error. And if you have more precise sensor, you just better know how much mileage you have. And this already saved like 10%. And I know about this work. Yeah, the medical sector and how people are now trying to push this direction also here in Stuttgart with movable or like transportable field applicable magnetometers for prosthesis actuation, as well as there are these surf magnetometers for brain activity detection out of the magnetic rooms. So not out of magnetic rooms, but at least at room temperature. That's quite exciting. So I would say there are a lot of opportunities, and yeah, but I think there will be much more once the sensors become better, and let's say more applicable, like more field ready. So far many of them are still in the lab.
Thank you.
Yeah, thanks. In quantum computing, and especially in quantum machine learning, we often hear the phrase, yeah, like this could work, but embedding the classical data is hard. We could use quantum data. Now we have some sort of quantum data. Do you see any applications of quantum machine learning in the research directions you presented today, and could this even maybe mitigate some of your problems with readout?
Yeah, thank you for this question. That's quite open question, I would say. I have to say that I don't understand much yet the prospects of quantum machine learning, but certainly normal machine learning is already quite useful. Just if you think about it, that this is more a generalized nonlinear functional, which you can train because you know the endpoints. This is already heavily used, and people try to use it for optimization of control sequences, analysis of the data, as I showed you. Like if you have a complicated output signal, you can predict what is possible. Then also people try to use machine learning models to invert non-analytical functions where you know the forward propagation, but you don't know the backward. And in terms of, let's say, relationship to quantum or using the information from the sensors to use, I know that at least there is a second handshake possible. For example, this spin model, which we reconstructed now. So this is like in the very end. So this is already quite useful for quantum chemists like DFT, because we know now with atomic precision of the lattice which spins are here, and we also know the hyperfine coupling, for example, from this point to this point. So this means that we give them a very valuable information about the wave function. And this wave function is exactly what they're trying to calculate, but they don't know the answer. And now we give them the answer. They can kind of close loop optimize it, and then they have a very precise understanding of what's going on. So yeah, and the second handshake is, this is not yet quantum machine learning, but coming from the other side, machine learning is now heavily used for DFT as well, because you can train some solvers on existing models such that they can predict non-known. And this is where this meets for now. I don't know if this answers your question.
There's another question from the online audience. You mentioned that there are already classical magnetometers that are used on drones applications. Would this be possible with quantum-based magnetic sensors in the near future?
Certainly, yes. Definitely. Thank you for the question, by the way.
You mentioned that the reading of brain signals is already sort of in reach. What would you say, how competitive to other approaches like Neuralink, literally putting wires into your brain? How competitive is it to do this approach?
Mm-hmm. Yeah, thank you for this question. So the magnetic encephalography of brain signals is actively happening. So you have two ways for now. You have the atomic vapor cell, and you have squid-based magnetometers, with which people try to analyze it. I think still the biggest advantage is that you don't have to open a skull, so that's the biggest advantage. And the disadvantage is they are further away from the neurons, so you have less signal. I guess as here also, as I showed you here, you need at least once to do it the dirty way and you know, understand what's happening. And then maybe you have some surrogate model where you can, from the fingerprints, already recognize, okay, this is what is happening, and then just looking from outside is already enough. So I think it's complementary, it's not competing.
Okay, so I don't see any further questions. So I would say we thank Vadim again for his very nice presentation.
Thank you.
And so with that, I would also close the session. And also I would like to say that on the next Quantum BW colloquium will be on the 30th of November, and it's given by Aparita Singha from the TU Dresden. And the topic of her talk will be NV magnetometry, challenges and opportunities for quantum sensing experiments. And thank you all for joining today, and bye.